Hello people from the future, welcome to Normalized Nerd. In this video, I'm gonna be talking about K-means clustering. It is an unsupervised learning algorithm and I'm gonna explain all the conceptual details of this algorithm, and at last I will show you how you can code it from scratch using Python. If you are new to my channel, then please subscribe. I make videos about machine learning and data science regularly. So let's get started. First of all, we should know what is clustering. Well, it is very close to classification, but there is an interesting difference between them. Well, the difference is while we classify something using our machine learning models, we usually have one vector that is called y, and this is known as ground truths. Well, this vector usually contains the labels of the classes. So for example, if this dataset would be an example of classification dataset, then each point would have a y value, and that y value would tell us the class that this point belongs to. Okay, but in this clustering problem, we are not given this y value, so we don't know initially the class labels of our data points. We have to figure it out by ourselves, and at last we should be able to assign a class for each of our training datasets, and when somebody will provide us with a new example, we should be able to tell which class should it belong to. Okay, so that is our end goal, and that's the difference between clustering and classification. The K-means clustering algorithm is quite similar to the algorithm that we have studied in our last video, that is KNN algorithm. So I would recommend you to check that video also, because in this way you will be learning two algorithms at the same time, and keeping these two algorithms at the same time in the back of your mind is probably a good idea. Okay, so let's jump into the steps of K-means clustering. Well, the first step says choose K points randomly. This K is actually the number of clusters that we want to define on our dataset. As you can see, in this case, 3 would be a good value for K, because you can cluster these points, you can cluster these points, and you can set these points. So K is equal to 3 is a good number for this dataset. But the problem is, in many cases, we can't visualize our dataset, so we don't know what is K. And I will show you how to find this K. Let's follow this instruction and take 3 points on our dataset randomly. Okay, so let me take this point, and I'm also gonna color code it. Let me take this as a second point, and let me take this one as the third point. Okay, and I'm gonna call these points centroids. Well, why I'm calling these centroids will be clear in a moment, but now let's look into the next point. Okay, this point says assign classes with respect to nearest centroids. For example, this point will be assigned blue class, this point will be assigned blue class, this one also, and here the points will be assigned green, and here they will be assigned white. Now the third step says compute cluster centroids. Well, this step means to compute the centroids of each cluster. So for example, say these points are painted as green, and we want to find the centroid of these points. I'm doing the formula for 2D space because I have two features here. So x1 cg will be, that is just the x1 coordinate of the center of gravity or centroid, is summation of mass of a point times x1 coordinate, and in the denominator we will have simply the summation of the masses. Now we can assign unit mass to every point. So in that case, the summation of masses will be just the number of data points in that particular cluster. Okay, and in the same way, the x2 coordinate of the center of gravity will be, so after calculating these formulas we will have three centroids, right? Say the green centroid is lying somewhere here, and the blue centroid is lying somewhere here, and the white one is lying somewhere here. Okay, now comes the fourth step. This step says replace the old centroids with new ones. That means we are gonna neglect these three crosses, and our new crosses will be here, here, and here. So in this way we have just updated our centroids, and the last step of this algorithm says iterate these until stop. Well, these means these three steps, and stop is a stopping criteria. Okay, so there can be several stopping criteria. One thing could be the change in the positions of the centroids. For example, if the sum of the distances between the old centroids and new centroids is less than some small positive number, then we can stop. Now I have to mention a couple of details about this algorithm, but first let us see this algorithm in action. As you can see, we are first starting with this unlabeled dataset, and then in the next step we are initializing our centroids, that is denoted here by red stars, and as we are iterating over the three steps that I have just mentioned, the centroids are getting updated, and so are the point labels. So after 4 or 5 iterations, we have successfully clustered our initial dataset. Voila! Now let us go back to the algorithm and let me explain a couple of points. The first thing that I want to mention is the curse of dimensionality. Well, if you have followed my previous video on KNN, there also I have mentioned this point. Well, the concept is, as we increase our feature space, that is, as we increase our number of features, we need to look for a larger volume of this feature space to find the points. And in that case, as we move farther from a point, the similarity between the 2 points decreases rapidly. So in that case, the quality of the prediction decreases. So in K-means also, with the increase in number of dimensions, the performance decreases. Now let us discuss about the objective function of k-means. Well, you know that in every machine learning problem, we try to minimize a function which is known as cost function or objective function. So what is the objective function in k-means? What we are actually minimizing is very simple, and let me write it for you. It goes something like this. J, which is the general letter for objective function, is equal to summation over all the clusters, and inside we have another summation which is just the summation over all the data points. And here we have L2 norm of this. The square of Euclidean distance. Okay. So what this formula actually tells us? Well, this simply tells us that we want to minimize the sum of the distances of the data points from the cluster centroids. These are the data points that are in our training set, and these are the centroids. And if we look back to our graph, you can see that we are moving our initial centroids to the actual centroids of these clusters. So after we have done this k-means, the summation of the distances of the data points from the centroids will be minimized, because centroids are such a point from which the summation of the distances of all points are minimum. So that is the objective function in k-means, and we can minimize this thing by converging to the true centroids of the clusters. Okay. Now I'm gonna tell you a way to find this k. As I have told earlier that in some cases the k is given, but in other cases we have to find it manually. So to find this, there is a very popular trick which is known as the elbow method. Let me explain this thing very quickly. So for this we need to draw a graph. So this is our graph, and in the x-axis we will be plotting k values, and in the y-axis we will be plotting the j, that is our objective function or cost function. So for example, we calculate the objective functions for 10 values of k. So it will be k is equal to 1, k is equal to 2, 3, and so on, and there is 10. Okay. K is equal to 0 doesn't mean anything, because in that case we don't have any centroids. So basically the centroid is at infinity, so the cost function will be infinity. So the real thing starts from 1, and in this case we just calculate the summation of the distances of all the data points to that point, and say this value lies here. Okay. Then we run the k-means with k is equal to 2. Suppose it lies here, and then we perform this thing for 3 and for 4, 5, 6, and so on. Let me join the points like this. Generally they just do straight lines, so you can imagine straight lines also. So let us look at k is equal to 3. After k is equal to 3, the slope of this line has decreased massively. Up to this stage, the slope was really high, but after this, the slope has decreased. So this point is called as elbow point. I guess because this looks like an elbow. So what does this elbow means? Well, this elbow means after k is equal to 3, if we gonna increase our k, the cost function doesn't decrease that much as it was decreasing before 3. So it tells us 3 is the optimal value for k. It turns out that this vanilla k-means suffers from a very difficult problem. The problem is the trap of random initialization. As you can see, at first we are choosing k points randomly. Now while choosing these points randomly, we can choose the points very close to each other. We can choose the points very far from each other, or we can just choose something like this. This initial orientation of the k points can change the output clusters. Let me give you an example for this. In this example, we can clearly see that our k-means finds some wrong solution of the clusters, and this is due to the initial condition of the centroids. To avoid this thing, we can do mainly two things. The first thing is we can run our k-means algorithm multiple times with obviously different random initializations. In that case, we will consider only those solutions which have occurred more number of times and for which the objective function gives the lowest value. And the other way is to use something called as k-means plus plus. And if you are using k-means from a library, then chances are they have implemented this using k-means plus plus. Well, I'm not gonna go very deeper into the concept, but here's the intuition behind this k-means plus plus. Suppose this is your axis and you have chosen the first point randomly here. Now the next point you are not gonna choose randomly. You will use some kind of probability distribution. To be more precise, your probability distribution will make you choose your next point far from this first point, because it turns out that if the initial points are far apart, then solution clusters are better. And by this I'm concluding this conceptual portion, and now we are going to jump into the code section. First of all, as usual, I'm gonna import some of the libraries that will be necessary for this task. And I'm importing here NumPy, scikit-learn for making our fake dataset, then obviously matplotlib to plot the dataset, and pandas to make our life easier. Okay, so here I am making the fake dataset, and this is the same method that I have used in the last video to generate fake dataset for classification problem. You can see here that in that video I have used ytrain here, but here I have left it blank because in clustering we don't know the ground truths, so I have left it blank. And the number of samples is 500. That means we are gonna have 500 data points in our dataset, and the clusters is equal to 3. That means our dataset will gonna have 3 clusters, and we have to figure out the clusters. And then n features is 2, which refers to we will have 2 independent variables. That is, our feature space will be 2-dimensional. And to reproduce the results, you can use this random state. Okay, so let us visualize this data. And as I have told it many times, that this code is really not that necessary because you can copy it from anywhere. And this is how our dataset looks like. You can clearly see that there are 3 clusters, 1, 2, 3. Let's jump into the k-means algorithm. So to implement the k-means algorithm, I have written here a couple of helper functions, and believe me, with this helper functions your code will be much more readable and your life will be much more simpler. So the first thing is the first step of our k-means algorithm, that is initialize centroids. Here we have to pass the number of clusters, that is k, our dataset, that is x. First of all, I am making an empty array, then I am iterating for k times, and I am generating one random x1 and one random x2. Then I am appending them as a coordinate of a point to our array, and at last I am just returning this array. So it will return me an array which will contain 3 points, and each point will have 2 coordinates, one for x1, another for x2. And to generate random points, you can use this function random from NumPy, and the uniform means we are picking the random numbers from a uniform distribution. And you can see here that the range I am picking from is mean to max. So it will pick a number, a real number, from this to this. That is the lowest x1 coordinate of a data point to the highest x1 coordinate of the data point, and similarly for this x2 also. Okay. Now comes the distance function. Well, this is a very simple function to calculate the Euclidean distance between the points, and obviously you can use here Manhattan distance also, and I will actually recommend you to use that and see if you get some different result. Well, obviously you will get different result, but just compare the results. It will be kind of a fun exercise. Then I am doing this function, which is the second step of our algorithm, that is assign clusters. And here we have to pass k, x, and the array containing centroids. Okay, so this is an array. So first here I am declaring an array named cluster, and I am populating this thing with -1, and the length of this array will be the length of this x, because the ith element of this cluster will represent the class of the ith data point. Okay, and I'm looping over all the data points. I am initializing a distance array, and then I am looping over all the clusters, and here you can see that I am appending the distance between current centroid of this cluster and the current point. So after that we will have an array that will contain k distances, and we will just take the index of the minimum one. In that way we will know which centroid is closest to the point we are currently looking for. And once we have got the nearest centroid, then we are just assigning that class to our current point. And after this loop is done, we will just gonna return our cluster array. Okay, now comes this function, which is the compute centroids. This will take k, x, and cluster array. Okay, so first I am gonna initialize an array name cg array. Then I am looping over the clusters. Here I have again declared an empty array. Then I am looping over all the data points. Now look at this logic carefully. If the current point belongs to the cluster, then we are appending that point to this array. So after this loop is complete, we will have an array that will contain all the points from a particular cluster. Then we can just find the centroid by taking the mean, because in our case centroid, center of mass, and mean are all the same. And after this loop is done, we will have 3 centroids. Now comes the measure change. Well, this will help us to know when to stop, because this will just contain the sum of the distances between previous centroids and new centroids. And this logic is very simple, and for those of you who don't know the zip thing, well, zip thing actually helps us to iterate over 2 arrays simultaneously. Alright, so this is one array containing the previous centroids, and this is another array containing the new centroid. So we are looping over both of them simultaneously, and we are calculating the sum of their distances. Okay, after that this function just shows the clusters. Again, it is a visualization code, not much important. After that comes the Kmeans. Here's the real fun part, because you can see that because we have defined these functions, our Kmeans code is very elegant here. So here we have to pass k and x. So first we are gonna initialize our centroids, then we are gonna initialize our cluster array, then we are taking a variable cg change, which will help us in stopping criteria. Okay, so we are looping over these steps until our CG change becomes less than 0.001. In this while loop, the first statement assigns the clusters. Then we are showing the clusters in our graph. Then we are computing new centroids. Then we are measuring the change in the centroids. And this step is very important because you have to replace the old centroids with the new ones. Okay? And this is exactly what we have discussed in our conceptual portion. Finally, I'm just gonna run this K-means algorithm. So let us explore the result. So this is the initial thing. You can see that red stars represents the centroids, and initially only 3 green classes are there, and they are due to this star. And due to this star we have this orange class, and due to this star we have this blue class. So after one iteration, the points have definitely moved, and now we have got much larger area for green class, and the orange class has also shifted, and obviously the blue class has also shifted. Now the thing to notice here is that the centroid of blue cluster in this picture will be represented here because we have replaced our old centroids with the new ones. Okay, so in this case the cluster centroid will be represented here, and you can see this is very close, and all the other stars have also changed positions. And after a couple of more iterations, you can see the clusters are getting more clear. And after this iteration, we have successfully clustered our dataset. So that was all for this video, and you will find this code obviously in my GitHub repo. The link will be in this video description. If you have liked this video, please share this video and subscribe to my channel. Thanks for watching.